Welcome back. In this second segment, we're going to describe our first matrix algorithm, and we're going to study its time complexity. First, let me put up the matrix picture one more time so you remember the definitions of the diagonals and so on. Now, the algorithm we're going to describe, called diagonal summation, is simply going to take as input a matrix, a square matrix A of integers of dimension n by n, and the algorithm is going to return the sum of all the elements on the diagonal of the matrix A. So in other words, it's going to sum all of the integers in red here in this image. So let's write down the pseudocode for such an algorithm. The keyword function indicates that the algorithm does return a value. We choose a meaningful but short name such as diagonal sum. Then we list in parentheses the inputs to the algorithm. Here there's only one. It's a square matrix, an n by n matrix of integers. Let's call this input uppercase A. And then on the last, as the last component of the header line, we have the return type of the function, an integer, which is the sum of all the diagonal elements. So we're going to use a variable sum to store the running total of the elements on the diagonal. We initialize it to 0, and then we're going to go through all of the rows of the matrix. So the index I will go from 0 to n minus 1, and for each value of I, we're going to access the element A sub I comma I, and add that to the running total in sum. So sum is assigned a new value of sum plus AII at each iteration of the for loop. At the end of the loop, the final result is stored in the variable sum, and therefore we return that. Now let's start our analysis of the time complexity of this algorithm. Remember that the time complexity is defined by a function f of n, where n is the size of the input to the algorithm. So before, when we were dealing with sequences or arrays or one-dimensional arrays, the size of the input was clearly the length of the array. Here we have to think a little bit. So let me write it down as an explicit question. What is the size of the input to this algorithm? Well, it's the size of the matrix A. Now, the issue here is that how do we define the size of a square matrix? Well, one way to do it is, since the matrix has the same number of rows and columns by definition of being a square matrix, we just need one number to define the dimension of a square matrix. That's the number of rows. So that's what we're going to choose here as the size of our input. Is n is going to be the number of rows of matrix A. Notice the fact that the n in the time complexity analysis is the same as the name of the parameter here in the pseudocode is completely coincidental. This could have been called P by P matrix, and n in that case would have been equal to P. So let's say we pick the number of rows of A to be n. But that's actually not the only way to measure the size of the matrix. Another way, maybe an obvious way, is to consider the size of the matrix to be the total number of integers in the matrix. How many integers are there in a matrix of size n by n? Well, the answer is n squared. So we could have used that other quantity, n squared, as the size of the input. Now, if this confuses you, again, this could have been called a P by P matrix. So would be, in that case, n would have been equal to P squared. Either choice is valid. I'll let you do the analysis with this definition of the input size, but for the rest of this lecture, we're going to use the number of rows of the square matrix as a measure of the size of the input. So n from now on will be the number of rows in a square matrix. Now that we have defined the meaning of n in the time complexity f of n of the algorithm, let's go through our usual steps. First, we need to define or select the primitive operations that we are going to count. So what are the primitive operations in this algorithm? Well, we start with an assignment statement. So that's one kind of primitive operation. Then remember, in the loop here we have an assignment statement and also a comparison statement, or expression rather. So we could count comparisons. Of course, in the loop we also have an addition, since we have to increment I by 1, and we have an addition right here in the body of the for loop. So integer additions are the third kind of primitive operations we could choose. So which one are we going to choose? Well, it turns out it wouldn't make a big difference here. I'll let you check that on your own. So to make it a little bit different, this time we're going to count the additions to measure the time complexity of the algorithm. So what is the worst case time complexity of this algorithm? In other words, can we count the number of additions that this algorithm performs in the worst case? As usual, we will call this number f of n. Remember, n is the size of the input to the algorithm. In this case, happens to be the number of rows in the matrix. So there are no comparisons in this assignment statement. There are no comparisons in the last step either. All the comparisons are performed in the for loop. So the for loop is going to dominate the runtime of this algorithm, of course, because the for loop is the only part of the algorithm that depends on n. Notice this is a constant time operation, and so is this one. That's why it was fine to just choose the number of additions. Now the question is, how many additions are executed for each iteration of the loop, and then how many iterations of the loop are executed? So for each iteration of the loop, we have an addition right here in the body of the loop. And then remember, we also have an addition here at the end of the loop when we increment the I, or counter variable. So we have 2 additions per iteration of the loop. Now, how many iterations will this loop execute? Well, we go from 0 to n minus 1, so we have n iterations times 2 gives you a total number of additions equal to 2 times n. This clearly is big theta of n, so this algorithm therefore is a linear time algorithm. It's a very efficient algorithm. If you double the size of the matrix, you double the runtime. If you multiply the size of the matrix by 10, you multiply the runtime by 10. You can't really do any better here, because to return the sum of the diagonal elements, you must have to go through all n elements on the diagonal. So this is really an optimal algorithm here. Now notice when we perform this time complexity analysis, we never really had to worry about defining the worst case scenario. So you always have to make sure this is actually a correct analysis. In this case, notice the runtime of the algorithm is determined by the runtime of this loop. And this loop always executes the same number of iterations. And the work in each iteration is always the same, namely an addition and an assignment statement, regardless of the size of the input. So what that means is that there's no really such thing as a worst case or best case, because in every case, the number of iterations is the same and the work per iteration is the same. So if I had asked you the best case time complexity of this algorithm, you would have answered big theta of n. And of course, if the worst case time complexity and the best case time complexity are the same, then the average case time complexity is also the same. Make sure you understand why. As a final comment on this algorithm, I want you to think about what would have happened here if we had chosen the size of the input to be defined as n squared, that is the total number of elements in the matrix. What time complexity relationship would you have inferred? F of n in that case would have been what? Well, it still would have been the number of elements on the diagonal. But in that case, if n is a total number of matrix elements, then the number of elements on the diagonal is equal to what? Well, it would have been square root of n. So I want you to think about that, convince yourself that this is the case, and that in that situation, f of n would have been big theta of square root of n. But would that have really changed the runtime of the algorithm? Well, it better not, right? It's the same algorithm. It's just a different way of analyzing it. So how is it possible that, in this case, f of n is big theta of n, but if we had made a different choice here, its runtime, or f of n, would have been big theta of square root of n? I want you to make sure you understand there are no contradictions there, because the meaning of n is different in each case. And in the end, the square root of n squared is still equal to n. So the two results, even though they look different, actually mean exactly the same thing.